some papers on both sides of the classroom with some exercises. So you can go ahead and get started on those. Good morning, everyone. I hope you're doing well and that you had a good break. I have copies of a few problems that I want us to do to review cylindrical polar coordinates, and then today we'll continue with the Serret-Frenet basis, a new basis we're going to learn about. Okay, I'm just wondering, how did homework 1 go? Did it go right? Raise your hand if it was okay. Great. What about the problem sets? Are we working on them? Any major issues with the sets? Okay, remember you can always come to my office hours after lecture on Tuesdays and Thursdays, to Katerina's office hours Mondays, Fridays. She also has them on Zoom, right, online, and her exercise session on Wednesday. You can also ask questions on Ed, so please do solve the problems and solve more if you have time. Our midterm 1, our first midterm is going to be next week on Thursday, July 3rd, during class time. More information to come on what it's going to cover. I'll send an announcement this week. And homework 2 is already posted and it's due on Thursday. Homework 2 is basically animating the motion of a pendulum, a spring pendulum. Okay? So just want to review the cylindrical polar coordinates. So remember last time we talked about the polar coordinates, which were 2D coordinates for a particle moving in 2 dimensions, and the cylindrical coordinates, and that's the extension of polar coordinates in 3D. So if a particle is moving on a 3D curve, EZ points vertically upwards. It always points along, it's the same EZ as the Cartesians, and then ER and E theta are perpendicular to EZ. They point, or they are varying in the EX, EY plane. So as you see in this figure above, I'm taking blue, is not the best color, but that's what we have for now. ER, E theta is a rotation of EX, EY by an angle theta. So then we can have this relationship between the polar basis and the fixed basis. This matrix over here is actually a special matrix. We're going to talk about this later, but just a quick idea. This matrix is an orthogonal matrix. Its determinant, what is its determinant? Can someone calculate its determinant quickly? Right, cosine squared plus sine squared. It's cosine squared theta plus sine squared theta. So what is its determinant? 1. And it also happens to be that its transpose is equal to its inverse. We'll talk about this kind of matrix later on in the course. Okay? Now, please go ahead, take 5 minutes and draw the cylindrical coordinate system for each of the particles of mass m in each of these problems. So we're not solving the problems, we're just drawing the cylindrical coordinate system. Yes?
Sorry, isn't it rotational matrix?
What is it?
The matrix you were saying.
Yeah.
Isn't it rotational matrix?
It is. It is a rotation matrix, yes. We'll talk more about it. Maybe we'll even talk about rotation tensors, but we'll get to that. Okay. So please draw the cylindrical polar coordinate system here. Give it a few minutes. So I printed the paper so that you don't have to waste time to recopy the problems. You can just draw the bases. You don't need to solve the problem just yet. Do you need the paper?
Yeah, thank you.
Okay. Sounds good. What about this one? You're welcome. So it might be easiest to first start by drawing the position vector to the particle before drawing the basis. Okay, it's not on there yet. Just take the paper and draw quickly. Feel free to chat with your neighbors if you need to.
Sorry, you're setting your computer.
Consider a particle moving in 3 dimensions, 3-dimensional Euclidean space, tracing another wave. Okay. And we can write the position vector of this particle in terms of the Cartesian coordinates, in terms of the polar coordinates, as we saw just did. Let's do the Cartesians. R is x ex plus y ey plus c ez. Okay, so we have a particle moving on a random curve in 3D, and here we're going to use the arc length coordinate that we previously defined. So we defined ds by dt to be equal to the magnitude of dr by dt, or the magnitude of the velocity, in other words. That's the definition of this arc length coordinate s. Let's kind of recall what it means. I'll give you a minute and then I'll sketch here what it means. Okay. So if I have a curve, that's a zoom in of the curve, and I have my origin. This is my position vector at time t. This is my position vector at time t plus delta t. And this is delta r. Delta r, which is r of t plus delta t minus r of t. Now, this here is delta s, the arc length of the curve. So recall that we had this discussion, what would happen if delta r is very small? Its magnitude, what would happen to the magnitude of delta r as it's very small? And then what would happen to its direction? As delta t goes to 0, delta r becomes dr. And what does its magnitude become equal to? Ideas? Yes. It approaches 0. What about the ratio of the magnitude of delta r over delta s as t tends to? So as this becomes very small, the magnitude of delta r, what is it going to equal to? Delta s. So the ratio, that's going to be equal to 1. The magnitude of delta r is going to be equal to delta s. So it's true, both of them are going to go to 0 separately, but the ratio is going to go to 1. They're going to become equal. Okay? And delta r is also going to become tangent to the trajectory. So, and delta r is tangent to trajectory. Okay, maybe I'll try to prepare a small animation and show you how delta r becomes tangent to the trajectory. Okay, and you can try to visualize it. If I take delta r to be very small, kind of becomes tangent to the trajectory. So then we defined a unit tangent vector ET that is tangent to the curve, and it's a unit vector. We call the dr. So ET is dr by ds. This is our unit tangent vector. Raise your hand if you understand why this is a unit vector, why ET is a unit vector. Okay, so let me repeat. ET, if I can calculate the magnitude of ET, that's the magnitude of dr over ds. And the magnitude of dr is going to be equal to ds. So as delta t goes to 0, the length of this vector is equal to the arc length of the curve. Does that make sense? So again, does that make sense that ET is a unit vector? Yeah, any questions? Okay, so ET is a unit vector, and similar argument, ET is tangent to the trajectory. So ET is our unit tangent vector. Okay? Any questions? Oops. So we have this unit vector ET equals to dr by ds. We're probably going to be interested in calculating the velocity of the particle. So v is equal to dr by dt. That's by definition what the velocity of a particle is, the rate of change of the position vector with respect to time. Can I express that dr by dt in terms of dr by ds somehow? Yes, how? Using the chain rule. So I can write dr by ds, ds by dt. So I've used the chain rule. Okay. And what is dr by ds? Et. And what is ds by dt? The magnitude of the velocity, basically, the magnitude of the velocity, which I'm going to call v the speed. So v et. So we're building this new basis. It's called the Serret-Frenet basis. The first unit vector in that basis is et. We're going to need to add 2 more to get a 3D basis. But the first unit vector is et, and so far we can express the velocity very simply as being a vector along et. Okay? Now, if I want to do kinematics in this basis, I'm going to probably need to find the acceleration of the particle. And how do I find the acceleration of a particle? That's just the derivative of the velocity. Okay? So A is d by dt of v. So the derivative of that v et. Now, is v scalar changing in time? Yes, that's just the speed of the particle. It is changing in time. Okay. What about et, the unit vector et? Does that change in time? Yes, right? So as the particle traverses the curve, the et is going to change. The unit vector to the curve changes. So both of these are functions of time, so I need to use the product tool to take the derivative. V dot et plus v et dot. Raise your hand if you agree with my math. Cool. This is actually a very interesting expression. It says that the acceleration is the rate of change of the velocity, which has to do with the rate of change of the magnitude of the velocity, v dot, but also has to do with the rate of change of the direction of the velocity. So the acceleration is the rate of change of the velocity vector. A vector has a magnitude and a direction. So the rate of change of the vector has to do with the rate of change of its magnitude and the rate of change of its direction. So now we need to figure out what this et dot is. Det by dt. Okay. Let us see. Et dot is det by dt. I can write this as det by ds by dt. I'm using the chain rule. That's because I can express the unit tangent vector as a function of time, but equivalently I can also express it as some other function of arc length or location on the curve. And this we already said is v, the speed. So et dot so far is v det by ds. But I still do not know what det by ds is. But I can show that det by ds is perpendicular to et. And that's a trick that comes up a lot in mechanics. And that's the trick. We start by saying that et is unit vector. So et dot et is equal to what? 1. And then I'll take the derivative of both sides of this equation with respect to s. What's the derivative of 1 with respect to s? 0, right? It's a constant. The derivative with respect to s is 0. Okay, so that's 0. What about on this side? What is the derivative of et dot et with respect to s? And if you've never taken the derivative of a dot product of vectors, just recall that a dot b d by dt of a dot b is a dot b plus a dot b dot. So that's the derivative of a dot product. So then what is et dot et equal to? The derivative of that with respect to ds. What's my first term? Let's do it step by step. Det by ds dotted with what? Et plus et dotted dt by ds. And because the dot product is commutative, I can flip these two and they're going to be equal. So, and I'll get rid of the 2 and I'll get that det by ds dot et is equal to 0. So what does that mean? If det by ds dotted with et is equal to 0, what does this say about these two vectors? They're perpendicular, right? So these two vectors are perpendicular. That's great. Any questions? Cool. So we're going to define that vector det by ds is some vector kappa en. Okay? Where en is a unit vector. So repeating from the beginning, we have a particle moving on a random 3D curve. We defined ET, which is the unit tangent vector to the curve, is equal to dr by ds, and we can express the velocity as being along ET having a magnitude v, the speed along ET. If I want to calculate the acceleration of the particle, that's going to be equal to v dot et plus v et dot, involving this et dot term. This et dot we expressed as v det by ds, and et by ds we defined to be kappa en, where en is perpendicular to et. So en dot et is equal to 0. They're perpendicular. Does it make sense that I said, notice here, I didn't assume that det by ds is a unit vector. On the contrary, I said it's kappa times the unit vector. So the magnitude of det by ds is equal to what? What is the magnitude of det by ds equal to? Kappa, the absolute value of kappa. Well, technically, I'm going to take kappa to always be positive, and I'm going to say that det by ds is equal to the magnitude of kappa. Kappa, we call that the curvature. The curvature of the curve. And let me explain why. So again, kappa has to do with the rate of change, the magnitude of the rate of change of the unit tangent vector. So let us consider two curves. Maybe I'll consider this curve, and then I'll consider a curve like this. And I'll draw et along this curve. Et at time t, or et at arc length s, and et at s plus delta s. Okay? That. And I can draw then the difference between them. Delta et. Are you with me so far? That's delta et. Let me do the same thing for this curve. If that's et at s, and make sure I'm capturing the right side of the word. Okay, that's et of s, and that's et, say, of s plus delta s, and that's my delta et. In which case is delta et, its magnitude bigger? That case, kappa is bigger. So when the curve is more curved, when it has greater curvature, kappa is bigger. So that's our intuition behind curvature. If I had a straight line, for example, this is my et, and actually maybe before I sum these vectors, I have to put them at the same origin. So I'll move that here, and I'll sum, and that's my delta et. So let's be careful with delta et. And before I sum them, let me take them and put them at the same origin. So that's my, sorry, put them at the same origin, and then I'll sum. So actually the difference is more striking now, and it's more visible that delta et is perpendicular to et. Right. If I had a straight line, for all the points on the line, et's are the same, right? So what is delta et at any two locations on the line, on a straight line? 0. So the magnitude of delta et is 0. So what's the curvature of a straight line? 0. Kappa is equal to 0. Okay? And as the curve resembles the straight line more and more, it's going to have less curvature. Does that make sense a little bit? Okay? Right. We also define, or you might have heard of the radius of curvature, which is 1 over the curvature. So the radius of curvature, so that's the radius of curvature. So So basically what this says, what the radius of curvature says, is that if I have any point on a curve and I can look at the point just before it, the point just after it, and I can draw a circle that approximates the curve at that point. The center of that circle is going to be called the center of curvature. And the radius of that circle is called the radius of curvature. So again, for any curve, and for any point on the curve, I can look at the point just before it, just after it. These 3 points, they define a unique circle. I can draw that circle. This circle is called the osculating circle. The osculating circle. Its center is called the center of curvature, and its radius is the radius of curvature, rho. The inverse of which is the curvature. And ET, for example, here points like this into the curve. EN is perpendicular to ET, always pointing towards the center of the osculating circle. One more name, that the plane formed by ET and EN is called the osculating plane, and it contains the osculating circle. Any questions? We'll do some practice now. Yes?
Is the idea that you get kappa first because, or are there other, like, extenuating factors? Because it just looks at the moment like you can make the circle however big.
No,
But it has to be 1 over k.
Yes, it has to be 1 over k. The radius of the circle has to be that. And actually, there's a very nice animation that I linked to the website just before class of the osculating circle on a 3D curve. It's linked on the website, so please look at that animation. Okay, we also have an animation of the Serret-Frenet basis on different kinds of curves. So, other questions? Okay, let's do some practice. Let's take some random curve. I'll take a curve and draw the Serret-Frenet basis. Well, what we have so far of the Serret-Frenet basis, we have ET, EN is our second unit vector. Let's draw it on this curve. And notice how ET and EN does not depend on the location of the origin. It just depends on the shape of the curve. So on the curve, if I have several points on the curve, I can draw ET. So here I'm assuming that the particle is traversing the curve in this way, so the velocity is always kind of to the right. So this is my ET at different points on the curve. Now, if I want to draw EN, for example, at this point, how would I draw EN? It's perpendicular to ET, but should I draw it down or should I draw it pointing up? Down. Why? It always points towards the center of the osculating circle, or the center of curvature. Okay, you can think of ET here and ET at the point just after is like this. Put the two vectors next to each other and EN points perpendicular down. Okay, so EN is always going to point towards the center of curvature. For example, here EN also points this way. What about here in that case? Can you show me with your fingers where does EN point? Cool. EN. What about here? Yes. What about here? Like this. Okay, what about here? Yes, I think so. Did you notice that EN flipped between here and here? So there was a point on the curve where EN flipped. That's the inflection point. So at the inflection point, the curvature is equal to 0. Does anyone remember what what an inflection point is from calculus? Yes. The second derivative is equal to 0. That's right. The second derivative of the curve is equal to 0. So that's what's happening here. At the inflection point, the derivative is equal to 0 and the second derivative is equal to 0. The curvature is going to change. It's going to flip suddenly. So at the inflection point, particularly, the EN is not uniquely defined. At an inflection point, EN is not uniquely. EN is not uniquely defined because that derivative is not uniquely defined. Or basically that derivative is equal to 0. So, yes. Close to the inflection point, the curve resembles a line. So there are other instances also where EN is not uniquely defined. Can anyone think of an instance where EN is not uniquely defined? Yes. Exactly. When you have a cusp like this, also the derivative dEt by ds is not defined because the function is not differentiable at that point. So dEt by dn is not defined. So we cannot draw En basically at this corner. Yes.
So uniquely defined when the line is flat.
That's another point that resembles the inflection point scenario where dEt by ds is equal to 0. For a straight line, Et is always constant, so we do not know where the center of curvature is. It's basically at infinity. The curvature is equal to 0, the radius of curvature is equal to infinity. The center of curvature is at infinity. So also in this case, for a straight line, dEt by ds is equal to 0, and En is not uniquely defined. Okay? So I want you to look at problem set 7. I have copies of that here if you need them. So problem set 7, problem 340 or problem 7. This is it, and you might also want to take set 8. Okay, actually, before we move on to set 7, let's finish up our bases. So far, we have ET, EN, and I'm going to introduce this third basis, EB. Can anyone guess what EB is? Yeah, perpendicular to both of them. So what is it? ET crossed with EN. Just to complete the right-handed triad. So ET is the unit tangent. EN is the unit normal. And EB is the unit binormal. Binormal. So you can think of a particle moving on a curve, and ET is tangent to the curve, and EN and EB are both perpendicular to the curve. And going back to the expression of the acceleration, recall we had that A was v dot et plus v et dot, and et dot was v det by ds, and we said that's equal to kappa en. So that's equal to kappa v en. So then the acceleration becomes v dot et plus kappa v squared en. So that's the acceleration, expression of the acceleration in the Serret-Frenet basis. And we can check the units. The units of v dot, it's meters per second, meters per second squared. That's a unit of acceleration. The units of v squared are meters per second, and then that's squared. So what's the unit of kappa? Right. What's the units of kappa, everyone? Chat with your neighbor, make sure they have the right answer. What's the unit of kappa? Yes? 1 divided by, 1 over 1 divided by length. So that we have we have a units of accelerations here, meters per second squared. And you can also think of kappa as being 1 over rho, 1 over the radius of curvature, so 1 over length. That way. Okay? So that's our expression for the acceleration in the Serret-Frenet basis. And we can also do kinetics in the Serret-Frenet basis. I can write F equals ma. And I can express my forces in terms of the Serret-Frenet basis. Fn or Ft Et plus Fn En plus Fv Eb is equal to m. A is v dot et kappa v squared en. And that's doing kinetics. Again, kinetics is forces, sum of forces. That's Newton's second law, or the balance of linear momentum. We can do that at the Serret-Frenet basis. And how many scalar equations can I get from this vector equation? 3. How? By projecting it along which directions? Ex, y, az, but here it's easily projected along which bases? Et, En, Eb. So technically I can project this along any 3 independent vectors in 3 dimensions. But if I project along Et, En, Eb, I'll get that Ft is equal to mv dot, Fn is equal to m kappa v squared, and Fb is equal to what? 0. Notice how all the forces along the EP direction, they should sum to 0. Why? That's how the basis is set up. The basis is set up such that the velocity is along Et and the acceleration is along the other vector En. Any questions?
forces have different physical interpretations?
What do you mean different forces?
Like the different bases, like so you have an FOT, FN, FOB. Are they like different physical interpretations, like torsion versus
That's
some sort of
great. That's a great question. So the forces, they're like always the same. They're the normal force, the friction force, but sometimes you can express these forces more easily in one basis rather than another basis. So it's not a different interpretation of the forces. It's just a different way of, or a different basis to express the forces on. And sometimes some forces are expressed more easily in one basis than in the other, depending on the problem. And you're gonna see, that's a great question actually, because we're gonna mix bases in some problems, because sometimes it's gonna be easier to express some forces in Cartesian and some forces in Serret-Frenet basis, and we can mix bases, and that's why projection is important. Any other questions? Okay. Questions? Let's go back to set 7, problem 7. So what's happening here is that we have a slider. The 120 gram slider has a speed v 1.4 meters per second as it passes point A of the smooth guide, which lies in a horizontal plane. So here I drew the top view basically. So gravity points into the page. That's my top view, and that's, I think, the origin. That's point A. That's point B. And the slider is coming here with a speed initially equal to 1.4 meters per second. Slider, let's give it a mass m. Let's call this radius r. Okay. So the 120 gram slider has a speed v of 1.4 meters per second as it passes point A of the smooth guide. Okay, so this guide is smooth, no friction yet. We're gonna learn about friction on Thursday. But right now the guide is smooth and it lies in the horizontal plane. Determine the magnitude R of the force which the guide exerts on the slider just before it passes point A, and of the guide, and B as it passes point B. So basically we want to determine the force from the slider, normal force, the reaction force from the slider, from the guide on the slider at points A and at points B. Before we look at finding these forces, let us follow our 4 steps for solving kinetics problems. So the first one is going to be, we need to figure out our origin, basis, kinematics. So positive velocity acceleration. Second step is FPD plus expressed forces. Third step is writing the balance law, vector equation of balance law. Step 4 is the analysis. Okay. So this is a particle moving on a predefined curve. The curve is a straight line, then a circle. Usually when the curve is circular, it's equally difficult or equally easy to use polar basis and the Serret-Frenet basis. Let's use the Serret-Frenet basis here. So at the point B, how does ET point? How do I draw ET? So the particle is going this way. So how does ET point? Up, right? What about at point A? Right. What about EN? How does it point at B? Towards the center of curvature. Okay. What about at A? Why A is ambiguous, right? Because just before A we have a straight line, and just after A we have a curve. So just after A, that's easy. Just after A I can draw EN like this, right? But just before A I have a straight line. So EN is not uniquely defined. So in this situation what we do usually is I want to take EN before such that as I transition from the straight line to the curve, En is gonna change continuously. Does that make sense? So for example, how would I take En in this portion of the curve? Pointing down. So I have a continuous transition of En. That's what I find easiest. But it's not wrong if you take En to be differently, because En is just not uniquely defined. But you might need to be careful with that. Okay, so we defined our Serret-Frenet basis. That was our step one. When we use the Serret-Frenet basis, we do not usually need an origin. I could take my origin here. They've already, I think, defined that. Or they haven't, but I could take my origin to be here. And we'll see if we need that or if we need to change it. So the origin is not necessary. I'll have a position vector r from the origin. I do not know how to express r in terms of the Serret-Frenet basis. That expression is going to be problem dependent. But v, I can express it as v et. And a, I can express it as v dot et plus kappa v squared En. Is that all right? That would be my step one. Step two is what? We're going to draw a free body diagram. So please take a few minutes and draw the free body diagram of the box while I'm at A, or of the slider while it's at A, and the slider when it's at B. So the free body diagram, all the forces acting on the slider, and if you can write the expressions, please do that. Feel free to chat with your neighbors. Okay. So how many forces are acting on the slider throughout its motion? Two. What are they? The weight and the normal force. Now here the normal force is a little bit tricky. The weight is easy. The weight is acting just into the page, right? So this is weight into the page, and this is weight into the page. And here I have et and en this way. And here I have et. and En this way, and I can also draw EB. Did I draw ABY? ET cross En is EB. ET cross En is EB. So I guess this is wrong. Is that right now? Okay. What is the direction of the normal force? Is it just pointing, or does it have any component along ET? No, the particle is free to move along ET. What about along En? Does it have a component along En?
Yes.
Right. Does it have a component along EB? Yeah. So it's basically, you have to think of this like a roller coaster, basically. If you're on a roller coaster and you're moving, there's going to be a force from the roller coaster that's kind of perpendicular to your seat from below you, that's going to prevent you from like going down, but also a force sideways that's going to prevent you from veering off course or getting out of the cart. So the walls of the cart and the bottom of the cart is going to provide forces on you. That's what's happening here. There's the normal force has two components, one from along ET and one along En, from below and sideways. So the normal force, and that's true in both cases. So in both cases we have the weight is equal to minus mg EB, and the normal force has two components, NN along En and NB along EB. Okay, and notice the components of the normal force along N and B are different. These two components are different. Okay, we didn't learn about the friction force yet, but if we had friction in this problem, in which direction would it act? ET, right, along the motion. Okay, so usually it is the case that when you have a particle, that's a side note. Okay, and I have a YouTube video about this. But usually when you have a particle moving on a curve, the curve has one tangent, ET, and two normals, En and EB. Okay? But if you have a plane, the plane has one normal and two independent tangent directions. Does that make sense, kind of? So if I have a particle moving on a curve, the normal force is going to act along these two directions, En and EB, to restrict the particle from moving generally in 3 dimensions to moving in 1D, basically. It's moving along the curve in 1 dimension. One coordinate along the curve gives us the location of the particle. So 2 normal forces are needed, or 2 components of the normal forces are needed to enforce this constraint. So N, the normal forces along En, and along EB. And if we had a friction force, that would have components just along ET, along the direction of motion. Whereas if you have a particle moving on a plane, what would be the direction of the normal force? And here I do N is perpendicular to the plane and T1 and T2 are tangents to the plane. It would just be along N, right? The normal force would be along N. What about the friction force? We had friction resistance to motion along the plane. Yeah, the friction would have T1 and T2 components. F2, T2. Okay, and basically our surface doesn't have to be a straight surface. It could be a cylinder. Could be a cone, depending on whether you're moving on a curve or you're expected to move on a surface. The prescription of the normal force and the friction force are gonna change. Questions? Let's take a 10 minutes break and then we'll come back and continue working. Shall we do a break? Well, let's do a 5-minute break. I'm sorry. Let's do it till 11:25. Please go, stretch, and come back by 11:25.
We're not assuming, okay, we're not looking at it like this is in that case, it'd be going like the plane is kind of,
So go ahead, stretch out. Take a walk outside. I have a couple minutes. ET cross N is EB. More like ET cross N is EB. So it's kind of into, yeah. But you got the idea, I think. So if you're here, might as well finish up this problem. That's what we're gonna do now. Finish up this problem. So. Okay, great. So, reminding you of the problem, we have a slider that's tracing this path, and we wanted to determine the normal force acting by the guide on the slider at two different locations that were, let me see. So determine the magnitude R of the force which the guide exerts on the slider just before it passes point A and as it passes point B. Okay. So let's just do F equals ma. So we've done our step 1, step 2, step 3 is the balance of linear momentum. Balance of linear momentum, F equals ma. This applies to any point on the trajectory of the slider. The forces are the weight of the normal minus mg eb plus nn en plus nb eb is equal to ma is here, v dot et plus kappa v squared en. Ooh. Right. So what's the difference if I want to apply this equation at A or just before A? What's the difference gonna be in the balance law if I'm applying it just before A and then at B? Yes. No normal component. At no an n component. No normal component along the n. Yes, that's right. Why? There's no curvature, right? Kappa. What is kappa just before A? Yes. So kappa just before A, kappa is equal to 0. What about at B? What is kappa equal to? 1 over the radius of curvature, and the radius of curvature of a circle is just the radius of the circle. Okay, so kappa at B is equal to what? 1 over r. Does that make sense? So then, just before A, we have minus, rewriting the balance law, minus mg eb plus nn eb plus nb eb is equal to n v dot et, kappa is equal to 0. So the normal force n is just equal to nb eb, which is mg eb. There is no force along et, so I'll get that mv dot is equal to 0. That's what I get by dotting with et. And these equations I get by dotting with en and ep, and then combining. Should I do this step by step, or does it make sense that the normal force is this? Maybe I'll do it step by step. Okay, so if I dot with et, I'll get that 0 is equal to mv dot, right? If I dot with en, I'll get that nn is equal to 0. If I dot with et, I'll get that nt is equal, mb is equal to mg. So n basically is just mg eb. What can you say about, well, first, questions? That's an N. Thanks, sir. Other questions? So what's the rate of change of the speed of the particle at this point? 0, right? Because v dot is 0, so the speed is going to remain constant. And that's going to be the case throughout the motion. Notice that at B, so at B, I also have minus mg EB plus nn En plus nb EB is equal to m v dot et plus kappa now is 1 over r v squared En. Okay? If I dot with et, what will I get? V dot is equal to 0. So also the speed is not changing. That's true throughout the motion. Throughout the motion, V dot is equal to 0 and V is equal to its initial value. N dot En, I can calculate Nn is equal to m over r v squared, and dot EB, NB is equal to mg. Did I make any mistakes? So finally the normal force is m over r v squared En plus mg EB. And I'm not done yet. V squared is just its initial value. So mr, v0, mg, I know all of these. I can solve for the normal force. Sounds good? Questions? I want to look at the normal force at one more location. Look at the normal force just after B. Sorry, just after A. I want to look at the normal force just after A. So what is the radius of curvature just after A? What is the curvature just after A? The curvature of the path. 1 over r, right? Because we're on the circle. Kappa is 1 over r after A. So I'll get, it's going to be the same thing as for at B. N would be equal to m over r okay, so that's the normal force at A plus just after A. And recall the normal force just before A was equal to mgEB. Okay, and En and EB and ET, they point the same. Just before and just after, just before A and just after A, the Serret-Frenet basis is continuous. We chose it to be that way. So, and at A, or just before A, and just before A, at A plus and at A minus, the Serret-Frenet basis is continuous, right? So, what can you note? What do you notice here? The normal force just before A, the normal force just after A. Is it continuous? No, there's a jump in the normal force. this is our notation for jump. There is a jump in the normal force at A, and that's equal to NA plus minus MA minus M over R VV squared En. So there's a jump in the normal force. The rate of change of the force, or the change in the force, is going to change if it's going to cause a change in the acceleration. So at A, there's a sudden change in the acceleration. We know that kappa is going to change suddenly. Before A, the acceleration had no En component, and after A, it had a 1 over RV squared En acceleration component. So there's going to be a sudden change in acceleration. That's what we call jerk. And jerk is dangerous because these sudden changes in acceleration are going to create forces. And if the jerk is large, the forces are going to be large. So the cart is going to experience a lot of forces or sudden forces as it transitions through point A. And this comes up a lot in designing roads or roller coasters. So can you comment on the safety of a roller coaster that looks like that, which is basically a straight line connected to a circular loop? Do you think that a roller coaster like this is safe? No, why not? Because as the person or as the people rolling around the roller coaster transition from straight to curved portion or from curved portion to straight portion, they're going to experience a sudden change in acceleration. A jerk, sudden forces. These forces, if they're big enough, if the change in curvature is big enough, are going to cause maybe lethal forces. Lethal forces. Okay, the same thing could apply to if I have a highway and I'm designing a highway and I'm merging on the highway. I want the curvature of my merge to increase gradually. There is a curve, a known curve that has linearly increasing curvature, and that's called the Euler spiral or the Euler curve. It looks like this. It has linearly increasing curvature. It looks like this, which corresponds to the shapes of roller coasters you usually see. So on the website, again, I added a link to animations showing the Serret-Frenet basis, how it would suddenly change for the roller coaster that is a circle connected to a line versus the roller coaster that is a Euler curve or clothoid. Okay? Questions? So even if you're designing a slide for a child, you want the slide to transition or to have a gradual kind of transition of curvature. Okay? Great. Any questions? Before we work on our quiz, I just want you to pull back up the paper we worked on initially, the cylindrical coordinate basis paper, and just want to practice the particle moving on a curve versus a particle moving on a surface. So if you look at the last two problems, 367 and 3193. So in these problems, is the particle moving on a curve or is the particle moving on a surface? (367) and 3193, the last two problems. So the particle in these two problems, is it moving on a curve or is it moving on a surface? Surface, right? Surface. So how many components of the normal force is going to have? One component, right? What is the direction of the normal force in 367? Yeah, perpendicular to the cone, right? And what about in 193? Also perpendicular to the cone. What about the tangent for the friction forces? If I had friction, how many components would it have? Two components, right? What would these components be? So let me draw the 367. Okay, This is a particle moving on a cone. This is the direction of the normal force perpendicular to the surface of the cone. That's the normal force, right? What about the friction force? How many components does it have? 2 components. What are the directions of these 2 components? Parallel to the cone, and then what else? Into the page or out of the page. Okay? So I have 2 components of the friction force, FF1 and FF2. So the friction force has 2 components because both of these components are tangent to the curve. So it's along the surface of the cone, basically along E theta, if you remember how we drew E theta, and into the page. Along E theta is into the page and parallel to the surface of the cone like this. The same thing kind of applies for that cone. I have the particle here, I think. Normal force, and then the friction force has 2 components, like this and into the page. Or out of the page. We're going to need to solve for the direction of the friction force. But it has 2 components. Does that make sense? Questions? What about for the first problem? How many components of the normal force do I have? How many components of the friction force do I have? Okay, so how many components for the normal force? 2, right? Because where do these components come from? So I think we drew that tube, and I think we had ER, EZ, and then E theta. So what is the direction of the normal force? Along EZ, what else? Along E theta. So N has components N theta, A theta, plus NZ, EZ. It's a common mistake students do is that you say that both of these are equal and you make them equal to N. That's a mistake. Be careful not to do that. And then the friction force is along which direction? ER. Okay, so that's kind of like a particle moving on a specific curve. The curve here being the tube, but the tube itself is rotating. Okay, any questions? Okay, so let's get you working on your quiz. The quiz today is a little bit complicated, so feel free to ask questions. Chat with your neighbors. That's going to be a pair work quiz. And let's give it 30 minutes. If we need more time, then I'll give you an extension, but then I'll have to post a video just to complete today's lecture. And on Thursday, we'll work on springs and friction. Your next homework 3, is very interesting. So you're going to look at the helix, a helix, and you're going to plot the Cartesian basis, the polar basis, and the Serret-Frenet basis on the helix. You know the helix? So I think you should be getting papers. If you don't, let me know. Yeah, please put all the electronics away. Did you get a quiz? Missing? Okay, here you go. Here you go. Yes. So that's also an interesting problem. It looks at both the Serret-Frenet basis and the polar basis at the same time. Please put all the electronics away, your phones away, phones away. From this expression. Kappa v squared, right? And we said kappa is positive and v squared is positive, so kappa v squared is always positive. So what does this say about the angle between A and En? Right, because A dot En is the magnitude of A, the magnitude of En, and then cosine the angle between them. So that's already positive, that's already positive. The cosine needs to be positive. The cosine of the angle between them is positive. So what can you say about the angle between A and En? Is it obtuse? Is it acute? It's acute, right? So that helps you figure out where En points. You know it's perpendicular to ET. You know it's in the same plane as V and A. But also the angle between En and A needs to be acute. So I'm just passing around. I want to check everyone's drawing of ET and En. Draw ET and En. ET, so where exactly does ET point?
The direction of V.
Exactly, right. And En is this way because the angle between A and En is, okay. You have the same thing? EB out of the page? Right. So you have ER, you have eta, that's right. What about ED? Yes, draw it. And then draw En. Okay, where does En point? It's perpendicular to ET. And it's in the same plane as V and A. So it's perpendicular to ET and it's in this plane. But is it to this side or to the other side? Think about it. Let me know if you have questions. Dia? Where's your ET?
No, ET is going to be pointing along it.
Along V, right?
Yeah.
So yeah, you have to make that clear, and En is perpendicular this way, and the angle between En and A is okay. Cool.
How do I make it clear that it's pointing along?
So maybe draw it in the same figure, or draw V here or something.
Okay. Yes, we
Yeah. Oh, I don't think your ET is correct. Look at the definition of the velocity. So V is along ET. Okay, so ET is along the same direction of the velocity, right? And En is perpendicular to ET, and it's in the plane that contains V and A. So En is in this plane that contains the V and the velocity and the acceleration is perpendicular to ET also. So maybe that'll help you figure out where En points. ET and where's En? I argue that these ET and En, they're not perpendicular. So they should be perpendicular. ET and En.